Hi, my name is Jinri Kim, and I'm from Seoul National University. And today I'm presenting our work called SIGIR, which is content-based graph reconstruction for clustered item recommendations. So first, I'll start with the motivation. So collaborative filtering is a leading recommendation method, excelling at capturing user preference through the viewing history. So I guess everyone will know, but just to explain it, what I mean by this is if both users watch the middle video, they're considered as similar users, but the first video is only watched by her but not watched by him. The first video is likely to recommend to him. And recently, collaborative filtering has developed with graph neural network, which is the most explicit way to represent co-occurrence collaborative signals and captures the user taste. And by using high-order graph structure, it uses multi-hop neighbor informations. So what I mean by this is if the video on the right can be recommended to multi-hop users, for example, like 2 or 3 or more hop users. However, there's a limitation exists for collaborative filtering because if new items without any interactions comes into the system, because they do not have any historical data, they do not have any connected edges. Therefore, they're impossible to recommend. And this is so-called cluster problem, which is difficulty in recommending new items to cold items with no historical data. And this problem is critical in real-life situations because, for example, in YouTube, like more than 500 hours of video being uploaded each minute. Then our question is how to recommend new items without historical data. By using items content. So content-based model use a fluent item content such as video, audio, or text to generate content features. Then diverse CF mapping methods have been proposed to transfer content features to recommendation suitable features. And using our inner product, we can produce the recommendation score. And I'll talk about the diverse CF mapping method in the next few slides. Various CF mapping methods and their I'm going to talk about various CF mapping methods and their limitations. So previous CF mapping methods include MOP method or generated methods such as GAN or autoencoder. However, these methods are unable to capture higher-order collaborative signals and item features beyond direct consumption. What I mean by this is these methods do not use like neighborhood information and only rely on direct consumptions. Therefore, recently there have been an attempt to use graph neural network on item attribute graph to utilize the high-order collaborative signals. However, these methods are unable to capture the dynamics of the user-item interaction because it uses content-based high-order signals, not the interaction-based high-order signals. Therefore, the recommendation rely on assumption that if items share the similar attribute, the user will have preference on that item. And this means it cannot capture the user's fine-grained taste. So to tackle the previous problem, first we want to use the high-order collaborative signal and use graph neural network on user-item bipartite graph, not on item attribute graph. However, cold item does not have any connected edges. Therefore, we proposed the model called SIGIR that uses multimodal content informations and graph mask autoencoder structure to reconstruct the user-item interactions to capture the user detailed taste. And next, I'm going to talk about our method SIGIR in detail. So this is the overall model architecture, and it consists of 3 parts. First, the user and item modality goes as an input and fit into the encoding layer. Then using the user and item node representations, we will generate user item bipartite graph G. Then we'll make certain item as a cold item and mask all the associated edges to make mask graph G prime. Then using our novel approach, we'll reconstruct the edges to generate reconstructed graph G-rec. And this will feed into a GNN encoder and perform recommendations. And I'll talk about the detail in each step. So first I'll talk about the user item encoding layer part. So for user, the user item will go through embedding layer to produce the user embedding. Then item multimodal raw features will go through modality-specific encoder to produce each feature embedding. Then to produce the final item embedding, we concatenate it and process through MLP layer. And in this part, we train using modality alignment loss, which is contrastive loss, to learn multimodal relationship through self-supervision. And this loss make modality embedding of the same item to be close to each other. And next, I'll talk in detail about graph reconstruction part. So by using user and item node embedding produced from previous part, we make user item bipartite graph. Then we label certain item as a code item and mask all the associated edges. This process is to mimic the test phase where the code item do not have any connected edges. Then it processes through GNN encoder and edge decoder to get the edge probability. And I'll talk about GNN encoder and edge decoder in detail in next slides. Then we'll reconstruct the edge and generate reconstructed graph GREC. And in this part, the reconstruction loss is used to train, which tries to make GREC to be similar to G. So I'll talk about the GNN encoder in detail. GNN encoder update node representation using both its own and neighbor nodes. For user, we process through multi-layer GCN to get a diverse user preference. Then the user representation from each layer will be aggregated using aggregation layer to produce final user embedding. However, to handle the code items, the final item embedding is itself. Then we perform edge decoder to calculate the probability of edges between user and item. And using user embedding and item embedding from previous part, we concatenated and perform MLP to get the edge probability. And we connect the top K high probability user item relationship to generate reconstructed graph GREC. And lastly, we perform recommendation using item and user embedding obtained through GNN encoder. So by using a reconstructed graph GREC, this will go into the GCN layer again to produce user and item embedding. And the reason why we use GCN layer again is that we want the code item informations to be flowed to the neighbor embedding and vice versa to enhance the recommendation performance. And this part, we use recommendation loss, which is contrastive loss, to maximize the dot product between the same pair and minimize for different pair. So to sum up the loss in overall architecture, we have 3 parts and each loss is produced in each part. Then the total loss is summing up all the loss with the weight. And next I'll talk about the experiments. So for the data set, we used 3 real-world video data set, TikTok Movie Lens 1 million and Yahoo Movie. And for the content feature, we use video, audio, and text. And for the modality-specific encoder, we use VIT for video, AST for audio, and VERB for text. And the detailed data statistic of the experiment is shown below in Table 1. And we split the data based on item in a ratio of 70 to 15-15. And for evaluation protocol, we use recall at K, precision at K, and NDCG at K. And there are 4 research questions that we want to ask. So first research question is, how does CGRC perform compared to the state-of-the-art clustered item recommendation models? And the second research question is, we want to know how the different components contribute to the performance of CGRC. And next question, we want to know the effect of the hyperparameters. And the last question, we want to see how can the superiority of the CGRC model be demonstrated through the qualitative case studies. To answer the research question 1, this is the overall performance comparison. And as you see the table 2, you can see that our model CGRC consistently outperform the baseline models. And this is the evaluation of modalities and aggregation method. And for modality, whenever we use all 3 modalities, it shows the best result. And for different design choices within the mass graph encoder framework, whenever we use mean for user aggregation and concatenation method for edge aggregations, shows the best result. And next, this is the effect of the mass graph encoder structure. And what I mean by there is a graph encoder, it means that we utilize the GCN produced user embedding to encode the mask graph G prime. And what I mean by there is no graph encoder is we utilize the user embedding without processing through GCN. And this is also whenever we say there is MLP decoder, it means we utilize the MLP layer to calculate the edge probability. And when there's no MLP decoder, it means we utilize just the inner product to calculate the edge probability without processing through MLP layer. And as you see the result, it shows when we use graph encoder and MLP decoder, it shows the best result. And now I'm going to talk about the effect of the prediction method on reconstructed graph. So in here, without GCN, it means like we utilize the link prediction result for recommendation, so we didn't use any GCN. And the other method is we apply GCN encoder to the reconstructed graph with different layers of GCN. And as you see the result, the best results are shown whenever we used 2 layers or 3 layers of GCN layer. And this is the effect of the hyperparameters. So for hyperparameter, we use 5 key hyperparameters. Embedding dimensionally and the masking ratio, the weight factor for multimodal alignment loss, and the weight factor for reconstruction loss, and top K value for edge connections. And the result is shown below. And lastly, we perform the qualitative analysis. So for example, by looking at the user history, we can know that user 3315 prefers Steven Spielberg films such as E.T., Jurassic Park, Jaws, and so on. And our model also recommends the Steven Spielberg films, Saving Private Ryan. However, this cannot be recommended using only content because Saving Private Ryan is totally different content. But because our model can capture the detailed preference, it can recommend the content-wise different movies. And also we can see similar thing for user 784. And lastly, this is our takeaway message of the presentation. So our model SIGIR uses multimodal contents, information, and graph mask autoencoder structure to reconstruct the user item interactions. And this method, SIGIR was able to capture the user's detailed taste and effectively recommend the clustered items. And that's the end of the presentations. Thank you for listening.